right. Yes, welcome everyone to the Scaling Computing Performance session for this event. My name is Vivienne Sze. I'm a associate professor in the Electrical Engineering Computer Science department here at MIT. And I'm excited to talk to you today about some of the work that we've been doing in efficient computing for autonomy and navigation. This is done in collaboration with various folks all across MIT. I should highlight Joel Emmer, who is also a faculty member in our department that I collaborate with this on, and also Surtesh Karaman, who is a faculty in the Aero-Astro department here at MIT. Okay, let me move forward. All right, so we're very excited about the many possible applications for autonomy and navigation, but one of the key enablers for autonomy is the computing aspect. And in particular, if we look to applications like self-driving vehicles, computing is actually a significant challenge. So for all these self-driving cars, in order for them to navigate around the world, it needs to collect a lot of data to understand its surroundings. So it often has many cameras located on the vehicle. It might even have some radar or LiDAR to detect the depth of various objects, how far away things are. So let's say, in early prototypes, they're collecting about 6 gigabytes of data every 30 seconds to, understand its environment, to process this. And so in these prototypes, the amount of computing that's required to process this data in real time, because of course you have to react to things in the environment, can be in the order of thousands of watts. So for example, a vehicle like this had computers in the trunk that consumed, 2,500 watts of power. And in addition to the fact that this consumes a lot of power, it also generates a lot of heat, which obviously makes it very uncomfortable in the vehicle, and often it might need some water cooling. We also looked within our group, so self-driving cars are very promising. If they are successful, we would hope that it would scale up, these autonomous vehicles. And then if you think about scale or being widely adopted, the amount of compute is actually quite significant as well. So just as a reference point, let's say, not let's say, but like Facebook in 2021 reported that they do over 1 trillion inferences per day across their data centers. So inferences is doing an inference running a DNN, for example. If you were to look at an autonomous vehicle, let's say you had 10 cameras around to really get the 360 understanding of its environment. And each of these cameras are capturing images at the rate of 60 hertz or 60 frames per second. You need to capture at a certain rate to understand changes in your environment. And let's say you need to run 10 neural networks or basically 10 inferences on each of these images to detect various different types of objects or obstacles in the image to process it. For one autonomous vehicle, we're talking about almost 22 million inferences per hour driven. So, and then if you scale this vehicle up, so these days there's I think there's 1.2 or 1.5 billion cars in the world. Let's say autonomous vehicles are quite successful and you have 1 billion autonomous vehicles. That's going to be 21.6 quadrillion inferences per hour driven. Okay, so that's quite substantial. What I want to show here is that computing is a challenge for autonomy, and then if autonomy is successful, it's going to be a significant contributor in terms of the amount of compute that we do worldwide at the scale of data centers or beyond. Computing is also going to be a challenge when we consider the fact that for many applications, we also want to shrink down the size of the robot, for example, to something that can fit in the palm of your hands. I would also say that this is also relevant for applications like just AI if you want to put it on your phone. There you might have much tighter power constraints, often on the order of under 1 watt, and this is often because on these devices you have a limited amount of technologies that you can use to cool it. Furthermore, if these are battery-operated devices, you have limited energy. And the challenge is a lot of the existing embedded platforms that are used for autonomy consume much more power than that. The additional challenge that we face is that currently, transistors are not getting more efficient, right? So we've had Moore's law and Dennard scaling over the past few decades giving us smaller, faster, more efficient transistors, but we can see that this has really been leveling off over the past decade or so. So as a result, general purpose computing or microprocessors are not becoming more efficient, And so the only way to deliver the computational needs required for these exciting new applications is to turn towards specialized or domain-specific hardware to gain, improvements in both speed and energy efficiency. So we really want to think about how we can design these computers from the ground up. Okay, so if we're going to redesign the computers from the ground up, one question we might be asking ourselves is, well, where does the energy go? Because we're very concerned about the energy consumption. Both, as I mentioned, from a small scale for battery-operated reasons and from a large scale, maybe also for energy costs and carbon emissions reasons. So where does the energy actually go? Well, as it turns out, the energy is dominated by what we call data movement, right? So shown here is a plot that's showing the energy consumed by, let me just make sure, by various different operations. So we have a multiplication here for various different precisions of multiplication from 8-bit all the way to 32-bit floating point multiplications, shown in blue, and then we have additions here. And what really jumps out is that the energy cost to, so when you do a multiplication, you have 2 inputs and 1 output. And the energy cost to read those inputs, each of those inputs from memory, actually consumes more energy than it's required to do the multiplication itself. So for example, reading a 32-bit value from an SRAM, so an SRAM is a type of memory that you typically have on your computer chip, and a very small memory, in this case 8 kilobytes, it would be 5 picojoules of energy for each of the reads. In comparison to doing the entire multiply is 3.7 picojoules. And it's even worse if you're reading this data from a larger memory that's further away. For example, often we have what we call DRAM, which is dynamic memory that's situated off the computer chip, and that would be orders of magnitude higher energy consumption. So as a result, when we're talking about redesigning these computers from the ground up to become more energy efficient to enable these applications, we really need to think about addressing the data movement because it's orders of magnitude higher higher energy than the compute itself. And this becomes a challenge when we look at a task of autonomous navigation, because autonomous navigation actually requires a huge amount of data. So we already kind of alluded to the fact that we have a lot of sensors collecting a lot of the data. We also have to represent this data in a certain way so that we can actually understand what is in the data itself and analyze it. So for example, one of the important tasks that's involved with processing these visual data or these images that we're collecting around the vehicle is to be able to do what we call semantic understanding, which is to understand that, for example, this is grass, this is a person, these are trees, and this is a building behind, right? Often you want to do this at high frame rate, particularly if your vehicle is moving very quickly, so you want to be able to capture the fact that your surroundings are changing very quickly. You might want to also do this at high resolution because that allows you to see further away, right? So objects that are farther away will have more pixels so you can resolve them. And then often you might have to also handle different objects of different scales. So typically what we have to do is expand the data, in fact. So while an HD image has 2 million pixels, you might have to build something like an image pyramid so that you can detect objects of different scales. And so this will increase the amount of data or pixels here by 1 to 2 orders of magnitude. So we can see that this is certainly a challenge. Another aspect that you have to deal with when you're doing navigation is geometric understanding. So that's really understanding how far away objects are so you don't crash into them, rather than what they are. And then you might want to build a map of this. So it tells you, where are the roads, where are the places where there's no obstacles. As you can imagine, the longer you navigate for, or the further away you navigate for, the larger the map you build. And again, you need to manage this map size. It's going to be a huge amount of data. So hopefully it's very clear that, we just talked about data movement, and data really consumes a lot of energy, but the challenge here is that autonomous navigation requires a lot of data. So how can we handle this? So I'll show you a couple of key examples in terms of how we deal with this in various components of or different steps within the autonomous navigation process. One of the very first things that you have to do when you're trying to navigate is to figure out where you are. You need to localize yourself. Where am I in the 3D space? So this is often referred to as visual inertial localization. If you're trying to localize yourself based on images, so the visual images around you, and an IMU. So like that IMU might have an accelerometer, a gyroscope. Often you mount this on, let's say, a robot, right? And then if the robot is flying around, based on these two pieces of information, it can figure out where the robot actually is in the 3D space, right? This is also applicable to things like augmented reality and virtual reality as well, because you need to know kind of where your head is looking at. If you don't have a map of, if you don't know what your surroundings are, you might also want to build a map at the same time. So this is what we often refer to as SLAM, or simultaneous localization, figure where you are, and then mapping, which is building a map of the environment. Okay, so this is a very typical type of thing that you have to run on a robot, the very first step. So in collaboration with Surtesh, what we tried to do is demonstrate that you can actually perform this operation at very low power consumption by designing specialized hardware to do this. So this is this Navion chip that we developed. So basically it's one of the first chips that performs complete visual inertial odometry, which is the task that we just highlighted. At the front end, it can take in information from the camera, recognize certain features, and track these features across the images, so it can kind of give you an idea of where you are. It's going to also take measurements from the IMU, so the accelerometer and gyroscope. Since that data comes in very rapidly, it does some integration on that to summarize the key important features of that information, and then has a back-end optimization that fuses these two modalities together to kind of give you, an estimate of where you are in the 3D space. So here's the actual chip itself, Navion. You can see it's quite small. You can imagine you can mount it onto these small robots. It's 4 millimeters by 5 millimeters in a 65 nanometer process. It consumes, over 600 to 1500x lower power than a mobile or desktop CPU. And one of the key things, in addition to the fact that it's specialized, that allows it to be more energy efficient, is that we really focused on reducing the amount of memory that's required to do this type of processing. I should also highlight that this processing itself is still happening in real time. So, often one way that you can reduce the power consumption is you can slow things down. But in the task of autonomy, you can't slow things down because you still got to move. So in this particular case, we're still able to process images from a rate of 28 to 171 frames per second. Okay, so what is the key thing that allows us to achieve the energy efficiency? Really, it's really focusing on reducing the amount of data that's required that we need to analyze and store on the system. So for example, the very first thing is that we integrate everything on chip, because if you recall, what I was saying before was that it consumes a lot more energy to go to off-chip far away memory. So if you can integrate everything onto the computer chip, it's significantly lower power. Then the next thing is, of course, when we put everything on the chip, you don't want to have a huge amount of memory on the chip because that's also cost and power itself. So we apply things like low-cost frame compression. So for the images that come in, we do compress them so that we can reduce how much they're stored. At the same time, we have to be careful here because we don't want to distort them too much so that you don't understand the content of the images, and we don't want to spend too much energy performing the compression as well. So we have to kind of balance those needs. In the back end, when we're trying to optimize and fuse those two modalities together, we actually can exploit a lot of sparsity in that system. So basically, sparsity means when there's a lot of zeros, you can exploit them by either avoiding certain computations or reducing how much data you have to store there. And together with these two optimizations, we can reduce the amount of storage required for this type of functionality down to under a megabyte, so only around 854 kilobytes. Once you figure out where you are in the world, you might want to actually also have a better understanding of your environment. And there's various tasks that people want to do to understand the environment. So one is the task of what we call depth estimation. So given an RGB image, can you estimate the distance of each of the pixels? Of course, you can do this with an actual depth sensor, but a depth sensor can be very expensive because depth sensors often involve sending a pulse out, waiting for it to come back, and then based on the delay, that's how far the object is. Just emitting that pulse is very expensive. So it's even better if you can just predict the depth based on the RGB image. Another thing is, just like we said, semantic segmentation to recognize what is the ground, what is the plane, what is a movable object, and so on. It should be no surprise to many of you that the state-of-the-art techniques to do these types of tasks, to understand your environment, involve state-of-the-art deep neural networks. But the challenge here is that these neural networks require several hundreds of millions, in some cases billions, of operations and weights to perform the computation. So if we want to compare it to something that we all have and all use every day, so for example, video compression, which we all have on our phones these days, this is at least 2 orders of magnitude more computationally complex than that. So again, if we want to have this capability that allows us to navigate and to be as universal and ubiquitous as video compression that we have on our phone, we need to do something to address this computational complexity. The benefit is that if you look at deep neural networks, there are some properties that we can leverage. So one is that high parallelism is actually possible. So those of you familiar with deep neural networks, is that just a bunch of multiplies and accumulates that can happen in parallel. So high throughput or high speed is possible. The main challenge, which should be no surprise to all of you, is once again memory access is the bottleneck, right? So for every multiply and accumulate, every MAC, we need to have 3 reads and 1 write. So that's a 4-to-1 ratio in terms of memory access to compute. And in the worst case, you actually would try to avoid this ever, but if that came from each of those memory accesses came from DRAM, each of those accesses would be, orders of magnitude higher than the multiply and compute. But at the same time, there are properties that we can exploit to reduce the amount of data that we need to move from memory. In particular, we want to exploit data reuse, meaning that if there's any piece of data that we're going to use multiple times for multiple operations, can we leverage that so we only read it once and use it multiple times? As it turns out, for a lot of these neural networks, there's a lot of opportunities for this. So for example, for convolutional neural networks, which are widely used for image processing, you have convolutional reuse, where the same inputs and filter weights are used multiple times, just in different combinations across the image. You also often apply the same filter to the same input. So that means that the input activation can be reused multiple times across the different filters. And then finally, if you're processing multiple images, each filter weight can be reused multiple times across the different inputs. So there's these great opportunities. What you want to do is then build specialized hardware that will allow you to exploit that. All right, so just as a quick kind of review or summary, so typically a lot of these dedicated accelerators or dedicated specialized hardware for DNNs look something like this. You might have a processing element that does some kind of computation, in this particular case multiply and accumulate. It might have some local memory, which we call a register file, that's very small, let's say 1 kilobyte of memory, so it's very cheap to access from. These processing elements might talk to each other and share data. They might also share a global buffer, which would be larger, and then in the worst case goes to DRAM. Just very roughly here we show kind of what the energy might be like in these situations. So if it takes 1x to do multiply and accumulate, reading from this small register file, which is 1 kilobyte, is also 1x. Reading from neighboring processing elements is going to be 2x the energy, and it's going to be more expensive if you go to global buffer, it's 6x the energy, and then the worst case, you go to DRAM. So what you want to try and do is you want to, as much as possible, do most of the reads from this very cheap local memory. And so the challenging task here is to take this very large neural network, chop it up into smaller pieces so that it can fit in this register file, and then think of what is the order in which you want to process those pieces so you get the most reuse from this register file. So ideally, you move it once to this register file, and it's used multiple times for many operations. So that indeed is what Joel Emmer and I explored when we tried to embark on this IRIS project. And so there's actually a lot of research in this space looking at what we call the data flows. How do you efficiently move the data through the system so you can exploit a lot of this data reuse? What we worked on was a chip called IRIS that could demonstrate how we could maximize this data reuse itself. By exploiting a lot of data reuse, you can reduce the amount of data reads from the global buffer by 100x and from off-chip memory by over 1,000x. And this chip was we fabricated 65 technology, and when we compare it to an NVIDIA GPU at the time, it was 10x lower energy, about 1/3 of a watt. That's what you can do on the hardware side. You can also make some changes on the algorithm side too. So you can actually make some changes to the DNN itself to make it more energy friendly. And there's a variety of approaches that people generally use to do this. There's 3 categories. So one is the task of network pruning, which is basically setting some of the weights to 0. Anything that is set to 0, you can either skip that operation, because anything times 0 is 0. You could also reduce the amount of storage you need. You can also have efficient network architectures, where you take these larger neural networks and then decompose them into smaller filters. And you can also reduce precision, so going from something like 32-bit floating point to 8-bit fixed. Often a lot of this work focuses on reducing the number of operations and weights. But what's really important, if you remember the kind of the theme, is that we want to reduce the energy consumption and reduce latency. And so the question is, do these metrics of number of operations and weights impact these kind of system level metrics? But it turns out that's actually not a good proxy for the number of metrics. So for example, this is a plot from Google's mobile vision team. They're showing here on the x-axis the number of operations, and then the y-axis is the latency itself. And one would expect, as the number of operations increase, the latency increases. But then you can see cases where the number of operation is fixed, but the latency is a 2x swing. Or the latency is fixed and the number of operations is a 3x swing. So what this means is that looking at the MAC, or the number of operations alone, is not sufficient to predict the latency itself. Another thing is energy. So I think there's been a lot of work looking at making these neural networks smaller, meaning fewer weights. And the hope there is that having fewer weights allows you to reduce the amount of energy consumption. But as it turns out, the weights are not the only types of data that's moving through your neural network. There's other data, the input, outputs also moving through your neural network. So the energy, in terms of the energy cost, weights are only one component of it. You should also consider the data movement of the input feature map as well as the output feature map. So instead, what we advocate for is that it's important to design what we call hardware-aware DNN algorithms. So these algorithms directly target the energy and latency of the DNN and incorporate them in the design and optimization of the DNN itself. So for example, you can do what we call energy-aware pruning. So rather than removing the weights that are small, you try to remove the weights that consume the most energy. And as a result, you can get, when you just remove weights based on the magnitude or the size of the value, you get a 2x savings. But if you can account for the energy consumption of these weights, you can reduce the amount of energy consumption further. And this is all for the same accuracy or performance of the DNN. Similarly, this is some work that we did with Google's mobile vision team called NetAdapt, which is basically trying to really incorporate latency in the design of the neural network itself. And the idea there for them is that they wanted to basically have a neural network, plug in a phone, and then have, based on the latency projections, try to figure out a neural network that would run most efficiently on this phone with lowest latency without sacrificing accuracy. Another thing to also consider when we turn towards the navigation side is previously a lot of the work focused on, given an image, can you classify what the image is? Or what's in the image. But what we also care about a lot in autonomous navigation is, given an RGB image, as we kind of mentioned, how far away are these objects so we don't crash into them. And again, the motivation here is because if you could put a depth sensor like a LiDAR or radar on your actual vehicle, on your robot, but it consumes a lot of energy. So if you could just take a regular image, a regular low-cost camera, and be able to predict the depth, it's going to be very cost efficient or energy efficient. But of course, you need to run a DNN to do this. So this is a whole field of work doing this is called monocular depth estimation to do this. And so what we want to see is whether or not those techniques that I talked about previously, this like hardware-aware DNN design, can allow us to make this task also more efficient. So indeed it does. So shown here below is the frame rate on a Jetson GPU, and this is the accuracy, and so higher is better. And so you can see that applying a lot of those hardware-aware techniques to make the DNN more efficient allows you to basically speed up the processing by 10x without significantly affecting accuracy. And we were able to run this on an iPhone in real time at the actual conference itself. OK, so one last thing. So let's say now you're a robot, you know where you are, you understand your environment. Now you have to decide where you actually want to go next. Right? So this is the task of exploration. And so one way of basically deciding where you want to go next depends on what you want to do. One of the tasks is what we call exploration, where you want to kind of see as much new stuff as possible, so as much new mutual information as possible. So you might basically, given a map, these are the possible locations that you can go to. So okay, just describe this map. So the light gray indicates the regions that there's no obstacles. The dark black lines, if you can see, are the obstacles itself, so they're like the walls. And then the dark, medium gray areas are the unknown environments. And you want to kind of figure out where you should go to scan that to detect new areas of the map. So you have to make that decision. So a very principled way of doing this is computing what we call the mutual information. So you try to figure out the region that has the most new mutual information. You go there, and you go there and scan it, and then you would update the map. And here we have this robot that's running around doing this in real time. It's always trying to go to the region with the highest amount of mutual information to scan it. And you can see it's building the map in real time. So we would love to, do this very quickly, because obviously, how quickly you can do this means how quickly your robot can actually explore. The challenge is that though this mutual information will guarantee that you always go to the place with the most amount of information, it's very computationally expensive. So we need to do something to address its compute. As it turns out, very similar to DNNs, mutual information is actually very parallelizable, because in fact what you have is you have a robot that's going out and scanning all these beams, these depth measurements all in parallel. So technically speaking, you can process each of these beams in parallel. You can run them on different cores. And then you would just add them together. The challenge, of course, is that actually as you're processing these beams, they're going to be fetching information from an occupancy map. And that usually what happens is these occupancy maps, they're stored in some memory, and there's limited ports to those memories. And so you can only access a certain amount of data at a given time. So that's really going to be the bottleneck. So even though in this case, typically you have, for standard SRAM, you can only access 2 locations at a time. But you would like to run n cores, let's say like 16 cores. So this is going to be the bottleneck, the ability to deliver the data to these cores. And so what we did was we looked into designing a specialized memory architecture to satisfy this access pattern, right? So you can see here if, oops, I gave it away. If the robot is here, you want to maybe scan diagonally. And so the numbers here indicate, in terms of time, the access pattern that you have. So the question is, can we break up this map into separate memory banks so they can access those in parallel? And the key thing is that you don't want, for any given time, more than 2 access to a given bank. And so it turns out that a diagonal banking pattern works here. So if we put each of these different colors in a different memory bank, you'll notice that for any given color, the same number only appears twice for any given color, meaning it's only going to be accessed twice for any given time period. And by doing this, by specializing, or basically aligning the memory banking to the access pattern, we can significantly speed up the processing such that we actually can compute the entire map that you're trying to map in under a second. So this is 2 orders of magnitude speed up. And this is the first time, this idea of using mutual information to explore is something that roboticists would have always wanted to do, but they couldn't do based on the compute. And now this actually makes it feasible in real time for the first time. So to summarize, efficient computing is really critical for the advancement of autonomous navigation, autonomous robots, particularly at the smaller scale. In order to meet these demands, we really have to redesign the hardware from the ground up and really focus on data movement. And then finally, these specialized hardware create opportunities for the co-design of both the algorithms and the hardware together. And so basically allows you to do, by jointly optimizing the 2 of these together, it opens up opportunities that you could not achieve with each of these alone. It opens up opportunities for the future of robotics. Thank you very much. And I want to acknowledge all my collaborators and the students and our funding agencies. Thank you. Okay, and then also if you want to learn more, we have a whole website focused on particularly the autonomy aspect of this work. Okay. Any questions? Sure, go ahead.
If you have any questions, please open up to one of the mics.
Hello. I was wondering when you were mentioning the transistor's limits, do you think there will be some new technology that replaces a transistor or works with it in a new computer architecture? Thank you.
Oh, sure. So your question is more about the end of Moore's law. Is it really ending? I think it depends on who you ask. I think it's increasingly becoming more challenging to shrink down the size of the transistors. I think there's a lot of emerging technology that people are investigating, including here at MIT, new devices to try and complement traditional transistors are becoming more difficult to shrink down, though there's people working on it. There's people trying to introduce other types of transistors and devices that can also serve different purposes. There's also a work of trying to better integrate the memory, the compute and memory closer together, because we just said data movement's very expensive. And so if you can integrate them closer, you can reduce the energy cost of moving it around. You can also increase the memory bandwidth. So I think from all factors, people are working from different angles.
Hi. So when you showed the energy pruning and the effect it had, and you were able to show that it was much better than the earlier technique, did you measure the effect that had on the performance?
On accuracy, yeah. So that's for the same accuracy, okay, cool. Right? So I think the main idea is that given a neural network, there's many ways to achieve that accuracy, right? And so you're trying to find the neural network that consumes the less energy. So this allows you, since you're targeting energy, you might as well consider that while you're removing the weights. You should check like how much energy is this going to actually take. And
what are your thoughts on like if you were to like continue down that path of energy pruning, like how would it affect the accuracy? I know you kept the accuracy level at the same benchmark, but what are your thoughts?
So in all cases, the more you prune, the more, or the more you modify, the more the accuracy will go down eventually, right? So the question is just more, what are you considering when you're removing these weights, for example? Thank you.
Hello. Do you think that moving towards generally more specialized hardware is the direction, away from like the CUDA x86 general hardware towards the more specialized things is what we need to do in robotics?
I think it depends on the application and how tight the power consumption is. So certainly if you have very kind of, you have known algorithms that you want to run and the power constraint is very tight. So for example, that Navion chip we showed would also be very applicable to AR, VR. And in that case, you have a very tight power budget because you have to wear it. And if you want to run the processing on a wearable device, the power budget's very tight. So there you need to specialize. But I think it's a whole spectrum. When you say specialized, like how specialized are you? You could be, another term that's commonly used is domain specific, right? So then you have some flexibility within that domain itself. So a very common thing for that is deep neural networks, right? So you're not so specialized that you only run one neural network. You run like a domain of neural networks. So you have some flexibility there, but you might not be as efficient running or able to run other tasks. So there's a fundamental trade-off between efficiency and flexibility, and where you lie on that spectrum depends on your application and the demands of your applications. For example, the efficiency that you require.
Thank you.
Thanks.
Let's do one last question.
Sure. Thanks for the talk. I was curious if this sort of idea that moving data around is generally more expensive than like computing on data, if that's true in sort of other places as well. So like maybe I understand it's true on my laptop, but is it true like as you scale up to like a big data center? And then I'm also curious if you happen to know if it's true like in a natural system like the human body.
Yeah, so the principle behind, at least from an electrical system, it will be true in the sense of like generally speaking, your energy cost to move something is the capacitance times voltage square. And it's usually the capacitance. So the further away you are, the higher the capacitance you need to charge, right? So if the wire goes further, there's going to be higher capacitance you have to charge it up. That being said, there's been a lot of work on using optical computing, and the idea there is then you're more independent of the distance. So there's a lot of work. I'm actually here at MIT and various spin-offs that also look at optical computing for that particular reason.
Thanks.